This question becomes pretty simple if you use the trick, otherwise it becomes a bit lengthy. In this question we have two rods of area of cross section A1, the natural length L1 and the Young's modulus to be Y1. Similarly for this rod we have A2, L2, Y2 and a mass M is hung from the lowermost rod. We need to find out is the motion of this block an SHM, and we need to find out the time period of the SHM. Now the motion of this block will definitely be a SHM, because as I told you, a rod with a given Young's modulus area of cross section and a natural length always can be treated as a spring of spring constant YA upon L. Therefore we redraw the system. This is a trick and the best way to solve the question and solve it faster. This spring becomes one spring and then another spring attached in series to that spring, and we have block of mass M over here. The spring constant of this spring is K1, that is equal to Y1 A1 upon L1, and the spring constant of this spring is equal to Y2 A2 upon L2. Now we know that whenever two springs are in series and there is a spring block mass system in the vertical direction, then the motion is definitely an SHM. Now to find out the time period of this SHM, we apply the formula for combination of two springs in series. Now the formula for combination of two springs in series in SHM comes out to be equal to the formula for resistances in parallel. Therefore we write the resultant spring constant is equal to 1 upon K is equal to 1 upon K1 plus 1 upon K2. The final answer comes out to be K1 K2 upon K1 plus K2. This is K equivalent. That is an equivalent spring which can replace these two springs and produce the same SHM with same time period. Therefore we can replace this system by a single spring of spring constant is equal to K equilibrium and a mass M here. The time period of this is 2 pi root over M by K. As we already know, this is K equivalent. Therefore this is equal to 2 pi root over M upon K1 K2 into K1 plus K2, where the values of K1 and K2 are equal to, K1 is equal to Y1 A1 upon L1, K2 is equal to Y2 A2 upon L2. So we feed in the values here to get the final answer for the time period of the motion of the block. This is the simplest and the best solution for this question. If you do not, you should do it this way. Otherwise the other method you could have adopted is that you could have assumed this to be the equilibrium position of the object, displaced this by a displacement x, and then found out the stress strain and then applied the formulas to get the time period and the resultant force acting, the restoring force on this object, and then the time period by that method. But that is a very silly method to do, because we already know that a rod can be replaced by a spring constant of spring constant is equal to y into A upon L, where y is the Young's modulus of the object of the rod, A is the area of cross section of the rod, and L is the natural length of the rod. So this is the final answer, 2 pi root over M into K1 plus K2 upon K1 K2, where K1 and K2 have values equal to Y1 A1 upon L1 and Y2 A2 upon L2.